In fact, you can prove, like if you have some expression with Boolean values in it on the left-hand side, and a different expression with Boolean values in it involving the same Boolean variables, then you can show that the left-hand side equals the right-hand side if the two sides have the same truth table. Right? So using a truth table is a way to prove an equation, that the left-hand side equals the right-hand side. Right. Okay. Now these statements now, so these variables, you can let them represent a statement. For example, so let P be the value, the Boolean value, in other words, true or false, right? That is T or F, true or false, of a statement. The sun is shining. Okay. So that's your statement. Just a sentence in English. The sun is shining. Now, if that's true, P. Now remember what's P? P is the Boolean value of this statement. In other words, is it true or false? So P is true or false about this statement, the sun is shining. Okay? And Q, that's the Boolean value of a different statement. For example, today is Monday. Well, it doesn't really matter. You could be watching this any day of the week. Alright? So now you can combine the two Boolean values. Like here, this would be P and Q. So that would be the truth value, in other words, true or false, right, of a combined statement. So this combined statement, like the sun is shining and today's Monday. Okay, so you're putting two statements together, and the truth value of this combined statement would be this, P and Q. Right? Because if the sun is shining and today is Monday, then this whole thing is true. Right? So if that's true and that's true, then using the definition of conjunction, and using the and truth table, if you like, this would be true. Now, if either one of these or both is false, well, this will be false. Okay. Now, this P and this Q here in this and operation, the P and the Q here, they get called operands. Right? Why is that? Because they're the things that you operate on. Right? So these are the two operands in this anding operation. Okay? Right? Now, let's see, 1, 2. Now, those three operations on Boolean variables, in the case of not, you're operating on just one Boolean variable. In the case of and or, you're operating on two Boolean variables. Now, those three, not, and, or if you use the longer terms, negation, conjunction, disjunction, same thing. They're not the only three. There are other operations that you can perform, but they are the main three. Right? They're sort of the dominant ones, the ones you use the most. But there are others, maybe used a bit less frequently, but they do exist. Now, one's called, I'll give you three more. One's called exclusive OR, usually written like XOR. Okay? And its symbol is, well, it depends on textbook and the author, and you have to check. But this author uses plus and a circle. Usually I see it like X and a circle, but anyway. So check the author, okay? So the symbol used by Sipser is this one, plus with a plus inside a circle. Okay. Now, so this operation, exclusive OR, note the word exclusive, like to exclude, like to reject or throw out, and you'll see why in a minute, why it's called exclusive OR. It's defined, it's the operation, you need two binary variables, A and B. So A XOR, or this, B, that combined Boolean value will be 1, will be true, when one of the two, A or B, is 1, but not both, right? Like once you've got one of them is true, the other, that excludes or rejects the possibility that the other one can be true, if you want your A XOR B to be true. Now, not this session, the next session, run out of space, I'll give you the truth table for exclusive OR. So exclusive OR is different from the ordinary OR in that with the ordinary OR, you got a 1, A or B, the value could be 1, in two possible ways. One of the two, A or B, was a 1, or, confusing. And the other possibility is both of them, A and B are 1. And you still get A or B gives 1. But with exclusive OR, if you have both A and B are 1, then the exclusive OR value will be 0. Okay, that's the difference. So it's like an OR, but it excludes, rejects, throws out the possibility that both of those Boolean variables, A and B, are 1. There, that's excluded. So if A and B are both 1, true, then the output, if you like, A XOR B will be 0. Okay, and you'll see that more clearly when next session when I give you the truth table. All right, so that's exclusive OR. Now here's the second one. We'll do two more. It's called equality, and its symbol is this way, like this sort of double arrow in two directions, like a two-way street. So the arrow that way and the arrow this way. So that's its symbol for equality. And so A double arrow B is 1, its value, when A and B have the same value. So A and B could both be 0, false, or A and B could both be 1, true. Okay? And the other two cases, and there's always just 4 cases when you have 2 variables, the other 2 cases are 0. In other words, when the 2 variables A and B have different values, like A is 0, B is 1, or A is 1, B is 0. Okay, and you'll see that in the truth table as well. Okay, so that's equality, and there's a third one called implication. That's the noun of to imply. Are you implying that blah blah blah? So to imply means to deduce, to conclude, yeah, all right. Now the symbol for implication is this arrow to the right, just a single arrow. Okay, so imagine then, and it too uses 2 binary variables, A and B. So you'd have like A arrow B. Now that expression, those 3 terms, A arrow B, that has a binary value, and that value is 1 when. Well, it's probably easy to get there. That value is 0 because only one case. The other cases are, the 3 other cases, it's 1. So A arrow B, its value, those three symbols together, the value of that combination of those three symbols is 0 when A is true and B is false, or A is 1 and B is 0. Okay? And that's common sense, because if A is true, B can't be false. Right? Not if A implies B. In other words, from common sense, if A is true, then B is true. Right? To imply, to say then, therefore. Right? So you come on this as kind of a therefore sign. So A is true, therefore B is true. So think of this as therefore, or hence, or so. Okay, you're deducing from A that B is true, or therefore B. Right? So if A is 1 and B is 0, if A is true and B is false, that doesn't make sense if you're deducing B from A. Because if A is true, and if B gets deduced from A, well then B must also be true. Right? So if that doesn't happen, then A arrow B is false. So it gets the value 0. And the other three cases, just A arrow B is 1 by definition. That's how you define this operation using implication. Right? So the next session, keep talking about Boolean logic. I'll give you the truth tables for these three operations: exclusive OR, equality, implication. I'll talk about something called the distributive law, that's sort of analogous to arithmetic. And towards the end of the next session, start on a whole new major topic: definitions, theorems, and proofs, which are a major topic. Many proofs in this textbook. So, very, very important topic. So, stop there.